Okay. So, has everybody played with a prism before at some point, either not even necessarily in class, you've just played either with an actual technical prism or with a piece of glass that acts as a prism?
No.
No? What does a prism do?
It basically acts like a reflection, but also like a frequency type thing.
Right? So prisms are the things that give you rainbows.
It causes the light.
So when it rains, like literally the little raindrops in the air act as prisms through the sunlight, generating rainbows. Like that's what this is. So what we are talking about here then is we're going to connect this rainbow effect to actual atomic structure, I swear. So this first thing says to color in as we see appropriate here. And I want to just point out a couple of things. You are, I hope, familiar with the order of the colors in the rainbow? Yes?
No, I need a refresher.
Yes.
You need a refresher?
No, I
OG
know.
did.
Roy G. Biv, thank you. Okay. So if you look at this, and the questions here are going to kind of, I don't have an orange or a violet, so sad. But if I look at this, when I pass light through a prism, I clearly separate out into the full rainbow, right? So I separate light into a rainbow of colors. Okay, but why do we have plurals here? Why does it make sense that we're saying this is reds and oranges and yellows and greens and blues and violets?
Because there are different shades of colors within those categories.
Right, there's not just one red. There are shades. There are what we refer to as hues, I believe. I'm sure all of my VA
Yes,
people can
correct.
school me. What?
I said you're right.
Okay. There are different shades, hues of each color. Because the thing to remember is that what we were referring to here is a spectrum. That is the technical name of what a rainbow is. It is a spectrum of colors. It is not actually a single red and a single orange and a single yellow. One fades into the other. And I know that they used to make in the art and design foundation class, they used to make students like actually work on blending one color into the next as part of like your little intro into color theory. And it's the same sort of thing. So when we are talking about all of these different colors, do they all travel at the same speed?
No.
No.
Yeah. Oh.
Do they travel at the same speed?
Oh, they
No.
do. Yes.
Yes, they
They
do.
do.
3.00 times 10 to the 8th meters per second equals the speed of light.
That sucks. Okay.
Right? That's what Einstein said you can't go faster than. So we've got the speed of light. Color is light. That's the same thing. Now, I will say that this is not the only amount of light, right? This is just what we refer to as visible light. There are, of course, light ranges beyond both of these colors that we can't see. Like, do you know what is right beyond violet?
Ultraviolet.
Ultraviolet. So right beyond violet, you would have ultraviolet. And then after that, you would have X-ray, gamma ray. And then on the other side, what comes right before red?
Infrared.
Infrared, right? The stuff in remote controls. And right before infrared comes microwaves. And before that comes radio waves. So you may not realize it, but all of those things are considered light, and they all go at the same speed. So what is different between them, however, is by far their energy and their wavelength. Their speed is the same, but not their energy and their wavelength. So if I look at that, which color of light is my highest energy color?
Red.
No.
Violet.
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 Violet. So here is the obnoxious thing. We always think of red as this like great, vibrant, like intense sort of color, and it is the weakest sauce there is. Like it is the weakest visible color. Violet, which often to us seems almost like pale, is actually highly, highly energetic. So the way to remember that fact is that staring into UV light damages your eyes, right? So all of these things, UV, X-ray, gamma ray, those are all very, very bad. Violet is closer to those things. Therefore, it is more energy. Infrared is a remote control. It does not do anything to you. It does not have very much energy. So red is your low energy. So your high energy here is violet, and your low energy here is the red. And if I look at the next question, question 6, which of these has my longest wavelength?
Red.
Red has the longest wavelength. Violet has the shortest. So we would call that an inverse relationship. All right, so for 6A is red and 6B is violet, and we're going to say that's an inverse relationship. If you have a short wavelength, you are generating lots and lots of energy. If you have a long, loping wavelength, that is not very much energy.
Oh, you can't see the bottom of your screen on the.
All right, so longest red, shortest violet. All right. Okay. All right, so I'm turning the page. Okay, so this is what I'm going to do for you in class on Thursday. But this is basically if you shine instead of a white light, which is, you know, like sunlight or a regular old light bulb, a fluorescent light or something. If you shine what is called a gas discharge tube, otherwise known as a neon light, right? Those big bright signs that are at the front of restaurants. If you shine a neon light and you look at it, it does not produce a full spectrum. You do not get a full spectrum, all right? So there is no rainbow. It is not a full spectrum. We get distinct lines of color. So hydrogen I'm just going to ask up here to begin with. Hydrogen, how many electrons does hydrogen have?
1.
1. All right, so it's got 1 electron. And out of that 1 electron, I see a red line, a blue-green, a blue-violet, and a violet line. So I see 1 electron. I get 4 lines of color. Off of that 1 single electron is able to do this. Now, boron down here, how many electrons does boron have?
5.
It has 5. All right, so it's got 5 electrons. And if I look, I've got a red, this orange, right? Blues, blue-greens, and then all these violets down here. So I have at least 1, 2, 3, 4, 5, 6, 7, 8. I have at least 8 lines of color. So before I go too much farther, does it seem that there is a relationship between the number of electrons and the number of lines of color that can come off?
Yeah.
Yes.
I'm very confused.
Well, because you don't know what's happening yet. I haven't explained it.
Question.
So I'm just saying that if you shine just a distinct element, one element, not a whole mixture of things through, you don't get a full rainbow. You get a distinct little spectrum of things. So these things here are called emission spectrums, or spectra, depending on how Latinish you want to get. And what we're going to see is these are essentially fingerprints. So if for some reason you were ever caught doing something wrong and you were taken down to a police station and fingerprinted, what is the whole point of them taking your fingerprints?
It's
To
unique,
identify
so you
you.
can be ID'd.
To
To
identify
see if
you,
you're at the scene.
right? So because your fingerprints, in theory, are completely unique to you. So if they are completely unique to you, that means you could be identified by your fingerprint. An element's emission spectrum is completely unique to that element. You can identify what is in a sample of something by looking at its emission spectrum. So, all right. So if I look at the, I don't really care about questions 7, 8, and 9. So if I look at question 10, which color of light corresponds to the shortest wavelength here?
Red
The shortest wavelength.
wavelength.
Violet.
All right. That's my
Violet.
shortest wavelength here, right? That 410 is my wavelength. So it is going to be violet. So same thing, shortest wavelength. And so therefore my longest wavelength is, again,
Red.
red.
Miss Baskin,
Yeah.
how did we identify that boron has 5 electrons?
How do you what?
How did we identify that boron has 5 electrons?
That's its atomic number.
Gotcha.
Yeah, but it gets real annoying with the B elements because there's a Br and a B. And so boron and bromine often get mixed up, but.
Wait, Miss Baskin.
Yeah.
So when you're talking about elements, their electrons, you're not how do you know when to consider
When to consider a charge? So right now when we're talking about stuff, everything we are talking about is talking about a neutral atom. So charges typically only come into play when they actually make bonds and into compounds.
Okay.
Okay. So which color of light had the most energy on this guy? Which one would have the most energy?
Golden
Violet.
question mark.
It should still be, most energy is still always going to be violet. Least energy is still always going to be red.
So it doesn't matter what the element is. Those are always going to be the same.
Yeah. Okay, now, if you look, does boron and hydrogen, do they have the same wavelengths of light in those colors?
Miss Baskin,
Oh,
No.
yeah.
are you gonna like send us like we'll post a video of this like after you're done?
I mean, of what I'm doing right now, like it's
Yeah.
being recorded.
All right,
Do you have this packet in front of you?
I don't because I
Mm.
can't find it.
Of course not.
So looking at this, they both have a red. Are they the same red?
No.
No, they're not the same red because this 656 and 625, those are not going to be the same hue or shade of red. Okay, so do they have the same wavelengths? No. All right, so they both have. All right, but they are two different wavelengths. It's a difference between imagining that you are working with a box of 16 crayons versus working a box with 64 crayons, right? You definitely have more options for red when you are dealing with a larger box of crayons. So we are not confined to just those single individual color of red. We've got more shades with that. So while they are going to be similar in color, they're not exactly the same, which means that you can use them like fingerprints. Okay, so how do these spectral lines support the statement that these guys are fingerprints? All right, each element's individual lines of color are unique to that element. If you have ever wondered how people look through a telescope at stars and can tell you what a star or a planet is made out of, this is how, because they can look at the color of light that is coming off of that star and see what specific spectral lines of color there are and say, oh, well, that star is primarily made of helium as opposed to hydrogen. And this is where I say my standard phrase of, I don't care about space stuff, but that is where that comes from.
How old the star would be if you can.
Okay, so now we're going to start tying this a little bit more into actually what the electrons are doing. So, looking at this next section. All right, electrons and protons. What do they do? Do they attract each other or repel each other? And first off, before you answer that, we should make sure we know what charges we are talking about. What is the charge of an electron?
Negative.
Negative. And a proton?
Positive.
Okay, so if I've got a negative and a positive, what are they going to do?
Repel.
Attract.
Attract.
Opposites attract. All right, opposites attract. So if an electron is close to the nucleus, all right, again, the electron is negative. The nucleus, because that's where the protons are, is positive. So as the electron gets closer to the nucleus, which thing are we going to circle? Attraction or repulsion?
Attraction.
Attraction again. And is that attraction going to get stronger or weaker as you pull them together? Think about how magnets behave. As you bring magnets closer together, does their attraction get stronger or weaker?
Weaker. Weaker.
Weaker? No, stronger.
Oh, my bad.
All right. So, because, let's see here. Attraction is stronger the closer things are. Right? If you're trying to hang something off your refrigerator, a magnet that is only holding one piece of paper, so it's only one piece of paper away from the refrigerator, is going to be much stronger than a magnet that is trying to hold 10 pieces of paper because it's 10 pieces of paper farther away. That's how to think about it. So if an electron is going to be close to the nucleus and you're trying to move it far, this is like pulling off a magnet. If I'm trying to pull a magnet off the fridge, does that require energy or does that give up energy?
Give.
Requires.
It requires. It's going to require energy to literally yank a magnet off. It's the same sort of thing. It requires energy to move an electron away from the nucleus. All right, so it needs to gain energy to move away from the nucleus. So again, if I have the nucleus here, my electron going farther away, that's what I'm talking about. I'm pulling the electron away from the nucleus. So the opposite means if I'm going from far to close, I'm coming closer to the nucleus. So I'm going from the electron is now moving towards the nucleus. As it's moving towards the nucleus, it is going to lose energy. Again, if you just think about like the nucleus as your refrigerator, an electron as a refrigerator magnet, it helps you make sense. So, is this diagram recognizable as a model of an atom to you?
Yeah.
Yeah.
Yes.
Most people, I feel like this is what you leave element or middle school or biology conceptualizing as an atom, right? So what is the dark dot in the middle?
The center.
And what do we call the center?
Nucleus.
Yeah, that's our nucleus. And depending on your teacher, these rings, right, these guys, you might have learned them as energy levels. You might have learned them as energy shells. You might have called them valence shells. These are various terms that people have used. Anybody learned something other than one of those three? I wouldn't imagine. That's fairly standard. I'm gonna pretty much use energy levels. So this number is just refers to the energy level. All right, so we number our energy levels. Number 1 is closest to the nucleus, and as you go up higher than that, you are farther and farther from the nucleus. Okay, so in this instance, this is my little electron, and it's going from here up to here. So what energy level did that electron start at?
I do.
It started here at the second circle, so it started at 2. So the electron started at n equals 2, and n just represents energy level. And where did it end up?
The 5th energy level.
5.
Yeah, I believe that's 2, 3, 4, 5. Yeah, so it ended at n equals 5. Okay, so to do that, again, thinking that my nucleus here is my fridge, and my electron over here is my fridge magnet. Do I have to put energy in, or am I getting energy out?
Putting it in.
Put
I am
energy.
putting it in. So it started at n equals 2, moved to n equals 5, and energy is absorbed to do that. Okay, so from the Edpuzzle video, it mentioned ground state and excited state. And those are mentioned up here again, ground state and excited state. Which of those states do electrons prefer to be in?
Ground state.
Ground state. Electrons like to be lazy. They don't want to have to do much. They want to be left alone in their ground state. In fact, they will not move to an excited state unless you do something to them. You have to give an electron energy to make it move to an excited state. So to go from a ground state to an excited state requires energy because they're boring. Now, when we're talking about light, most of the time that energy you are putting in to make the electrons excited is coming from electricity. So your light bulb right now that is like creating this image on your screen, or that is in your, above you in your house, those light bulbs are basically exhausted electrons because they're taking energy from the electrical socket, and that electrical energy is exciting the electrons inside that light bulb and making them go up to an excited state. But is it possible to stay in an excited state forever?
No.
So
No, it's unstable. So they are going to fall back down, and when they fall back down, they have to give that energy back off as light. Now, the unfortunate thing about the electrons trapped in a light bulb is they don't get to stop because you have left the switch on, so you have a constant supply of energy that is making them go up and down and up and down and up and down and constantly generate light. So it requires energy to go up into the excited state. So as we label here, this down here would be a ground state. Even though it's not all the way down at the bottom, we would still, it's the lower level, all right? And up here at 5 would be the excited state. And I'm going to say here that that is unstable. Okay, so now let's turn the page and take this back to hydrogen's little lines of color.
Miss Baskin,
Yes,
how come the first energy level isn't the ground state?
it would be the ground state if that's where the electron is.
Oh, okay.
Yeah, it's just basically when you are comparing the electron, it's like whatever the smaller number is, wherever it started is the ground state. The higher number is the excited state.
Okay, thanks.
Uh-huh. Okay. So let me get these all on one page. All right, so we said that hydrogen generated 4 lines of color. Those 4 lines of color are represented in these 4 diagrams. So to start off with, for each one of these, I want to identify where the electron is starting and where it is ending. So again, my electron is this arrow. Okay, so we're going to ignore that squiggly line for just a second. So in A, what number of energy level did the electrons start?
6.
6. So we would say it's n equals 6. And where did it end?
2.
2.
Oh, 2.
All right. So for B, it went from what to what?
5 to 2.
5 to 2. N equals 5. And then for C,
4 to 2.
2.
4 to 2. And the last one?
3 to 2.
3 to 2. Okay. So then the thinking here is, am I going from excited to ground or ground to excited?
Excited to
Ground.
ground.
All right, so I'm going from excited down to the ground state. Does that require energy or does that release energy?
Release.
A release.
It releases, right? So this releases energy. How does the diagram show that energy is being released?
The little wavelength
The
coming off.
squiggly
A little
lines.
squiggly line, right? That is my released energy. This is light. That light ends up hitting your eyeball, and the rods or cones, I don't remember which one sees which color or thing. One's black and white, one's color. I don't know. Ask Dr. Nickerson. That light wavelength hits your eyeball and your brain processes it and says, oh, that's red. And that's what happens. That's how you actually see color. It's this process. So that being said, flipping back to here, our options of those 4 lines of color are red, blue-green, blue-violet, and violet. And so we need to identify which one of these is red, which one is blue-green, which one is blue-violet, and which one is violet. So the extremes are the easiest, the violet and the red. Which one of these seems like it would be the red?
One. Because it has the longest wavelength.
Yes, it is D because it's got the longest wavelength. Okay, so this is red, and I know that because it's got the longest wavelength. And you can see when you draw the wavelength out like that, this looks weak because it is weak. It's low energy. When you draw out the long wavelength, it's very low energy. So then the opposite is the easy one to pick out. Which one of these must be the violet?
A.
A, because this is super tight, right? So that's my violet because it's got the shortest wavelength. So then I have to figure out, I've got a blue-green and a blue-violet. So which one is going to be closer to the super short violet?
The blue-violet.
The blue-violet. So which letter is blue-violet?
B.
B. And that means that C by default is the blue-green. Okay, so while we've actually already done most of these things, right? Like we labeled everything there, and we said that this transition, are we absorbing or releasing energy?
Releasing.
We are releasing energy because my electron moved from, we didn't say high or low, we said it's moving from between excited and ground. Where is it going?
Ground.
Where does it start?
From excited to
Yeah.
ground.
So from excited, which is higher, to ground, which is lower. And so light is released. All right, and then we actually have very little left to do. So we actually did all of that because we did it all at once. So when it says transition, this means from what number to what number, all right? So the 1, 2, 3, 4, 5, 6. So which of the transitions in the diagram involved the most energy?
A.
All right. So it is A. So that would have been N equals 6 to N equals 2. So, and this involves the most energy because the electron is farthest away from the nucleus and more energy was required to put it there. So more energy is released when it goes back. Right? Think about it like if you're playing with a rubber band. If you just barely stretch out the rubber band and let it go, it, you know, like it's not going to do that much. But if you pull it way, way, way back, you know that it's going to release a lot of energy to when it snaps back. So it's that kind of notion. If I told you that a single atom of hydrogen cannot produce all 4 simultaneously, simultaneously meaning at the same time, why is it not possible for hydrogen to make 4 colors all at the same time?
It only has 1 electron, so it can only be doing 1 jump per time.
Right. So hydrogen only has 1 electron, which can only make 1 jump at a time. But if that's the case, then how does a full discharge tube give me 4 colors?
There are many hydrogen atoms.
There are many, all right, it's filled with billions of hydrogen atoms. So the last thing I want to do is actually question 25, and then we're done. I'm going to skip some others. Okay. So question 25. This doesn't work as well in paper and lines as it would in real life, but say these are my 4 different samples. Think of them as like 4 different suspects in a lineup. And then this is my unknown, and my unknown I'm saying is 2 of the 4. So if I'm a fingerprint analyst, how am I going to figure out which of those 4 is in the unknown?
Lining up the lines.
Lining up the lines. So this first line in the unknown comes from which element?
Helium.
It comes from helium. Okay, so that means I know that helium has to be in the unknown, because if I look, every single one of helium's lines is in this unknown. But is helium the only thing in the unknown?
No.
No.
No. So I've got to figure out who is giving me this line.
Hydrogen?
Hydrogen.
Hydrogen.
Hydrogen. And then I need to verify that all of hydrogen's lines are present in the unknown, and they in fact are. And I can clear the good names of lithium and sodium because their lines are not present. Now it's really obvious with lithium perhaps. Sodium gets a little tricky because of this line right here. The only reason I know that that line, which looks like it could be that line below, doesn't come from sodium is because the line right next to it is not present. And so if one of them is not there, then neither of them are there. You can't pick and choose which of the lines in your fingerprint get used, right? It's all or nothing. Okay. So on Thursday, I am actually going to use one of these spectrum tubes. I brought home my high energy spectrum tube, and I've got tubes for hydrogen, helium, and neon. And I have, it's not a prism, it's called a spectroscope that I think I've worked up how to hook it up to my computer through a document camera so that you can see in real time one of these spectrums being produced. And we're gonna go some more looking at an actual like active model to look at and see how the electron behaves and generates these little lines of color and talk about how the hell Bohr knew what was going on. So a couple of things to highlight. I am not assigning a new ed puzzle this week because that ed puzzle that was due last night basically covers 5.2 and 5.3, which is what we're doing this week and next week. So you have no new ed puzzle. So if you didn't do the one last night, we'll get it done and know that there's not another one coming. The flame test lab in your packet, we are mostly going to do that. I'm going to do it like I did last time, which is figure out a Google form for you guys to put information in. The difference is this one is not so much going to be you doing virtual stuff on your own. Like I have a burner and samples and we're just going to do it on my computer. Like I'm going to burn stuff for you, whereas you would have gotten to burn it on your own. But I couldn't send you home with little chemical lab kits. Sorry, but I brought it. I have my mobile meth lab down here of all of my own chemicals. So we're still going to do the flame test lab. You're going to get to see all the very, very pretty colors, and we'll talk about fireworks and all that sort of stuff. I know that the end of the video that I did and the end of section 5.2 goes over some calculations. We're going to deal with calculations next Tuesday. So the day for us to discuss calculations and nu and lambda and wavelength and frequency and energy and Planck's constant and all that stuff that it's in that reading guide and those sections, that's going to be for Tuesday. So that's kind of what we have coming up. And that's it. So do people have questions? Otherwise, lovely to see you. So many people. I hope you got outside in the sun yesterday because it really was a lovely day.
I have a question.
Yes, question.
Why hot things like hot metals glow red? Because they're releasing a lot of energy, so the electrons from like the high frequency go to like the low frequency, and then they glow red.
Yes. So they glow red because they're taking heat energy, and that heat energy is actually exciting the electrons and making them jump and produce things. So it's not, it is a phenomenon that is kind of specific to metals because of how metals have a very loose relationship with their electrons, shall we say. So they don't quite have some of the same obvious transitions that some of like the noble gases, which are, when you see a neon sign, it's called a neon sign because it's literally filled with neon. The noble gases have very distinct colors, but in general, all of the metals, because of their loose relationship with their own electrons, they tend to kind of just be all in the same narrow spectrum. So you see a lot of glowing of red and then glowing, and then right as it gets hotter and hotter, it goes closer to like the oranges and then the yellows, and you know, like blue flame is hot flame, not orange. Blue flame is hot flame. So if you remember kind of that with your colors and your energy, it kind of makes sense.
Other questions?
Yes, Kamai.
If I turn in the ed puzzle today, do you take off points too?
Girl, I ain't taking off points for late work.
Oh, okay.
I have some people who are like, yeah, my internet was working fine, and then somebody was doing construction down the street, and our whole neighborhood has gone out. And I'm just like, cool, get it done when you get it done, because shit's happening. Like, okay, just communicate with me. Like, that's literally all I ask. Is just tell me what's going on.
Okay, I'll turn in today.
Okay, yeah, everybody's doing their best. It's fine.
Is so 5.3 reading guide is for Tuesday.
Yeah, it's super short, and I think I even say a lot of stuff in there. I'm like, yeah, that's cute, and it's some like higher level differential equations from college. Like, we're not talking, I mean, it's very short and skimmed through. And again, reading guides are for you to process what the hell is in the packet. They are no longer for you to show me or turn into me.
Okay, thank you.
Anything else?
Do you think unrelated, but do you think we're gonna end up like seeing each other again before the school year's over?
I don't know that we are, and it's sad. I don't know. I have a feeling with the way Bowser works, she is probably going to give like four-week chunks of information at a time and say, it's like, okay, so we're probably not coming back April 27th. And then she'll say, it's like, so our next planned date is this time. Like, I don't think they're just going to say we're not returning. But yeah, I don't know that we are. I'm very sad by this.
So, reading guide 5.3 was supposed to be done today, right?
No, 5.3? No.
I was confused.
Yeah. No, we're not talking about the stuff in 5.3 until next week. Cool. Okay, I'm going to kick you guys all out so I can process the video.
I'm here.
Josh. I saw you, Josh.
Thank you.
Yeah, look at your funky lights up there. Is that a purple light? What you got up in there?
They're violet.
So, and it makes purple, so I guess it's bisexual flag.
Oh, shut up. What do you use? Like a disco room? Okay.
Thank you for asking. Bye.
Uh-huh. Bye.